The first question in chapter 2 is about forming covalent bonds. So covalent bonding, remember, we have to have full outer shell, usually 8 electrons. So we need to look at these elements here to find how they can satisfy the requirement to get a complete outer shell. So to do that, we need to know the group of these elements, how many electrons are already in the outer shell, how many more is needed, therefore how many bonds is needed, because each single bond provides one extra electron. Remember that. So we can make a table maybe to do this. We have the group, number of electrons, so we have 4 criteria. The first one is the group number, and then the number of electrons already in the outer shell, number of electrons needed for the full outer shell, and number of single bonds needed for that. So for silicon, okay, you need a periodic table for this one. Silicon is in group 14, okay, there. So group 14, which means it has 4 electrons in the outer shell. So in order to get 8 electrons, we need 4 more electrons. Therefore, you need 4 single bonds. Okay. Silicon. Antimony, you have to find antimony is in group 15. And the number of electrons in the outer shell will be 5. Therefore, you need 3 more electrons, so it forms 3 bonds, 3 single bonds. Bromine is a group 7 element, group 17 element here. So 7 electrons in the outer shell already, so you need 1 more electron. Therefore, just 1 single bond. Hydrogen, the first element we know is in group 1 and it has 1 electron in the outer shell. Now to get complete outer shell for hydrogen, do we need 7 more electrons? No, because hydrogen is in the first row, therefore the first shell. Okay, and the first shell only has space for 2 electrons. Okay, so in order to get full outer shell, only 1 more electron is needed, because only 2 electrons gives full shell. So it only forms 1 bond. And selenium is an element in group 16, below sulfur. Therefore, 6 electrons in outer shell, 2 more electrons needed, 2 single bonds. So once you have this information, you can work out the simplest molecule you can form between silicon and bromine. Okay, so you can see silicon needs 4 more single bonds, but bromine only form 1 single bond. Therefore, how many single bonds, how many bromines do you need for silicon? Well, 4 of them. Okay, so silicon forms 4 single bonds. Bromine forms 1. Therefore, the ratio between silicon and bromine is 1 to 4. So you can satisfy all the bonds requirements, and therefore the compound should be SiBr4. Then you have to draw a dot cross diagram for SiBr4 to show how to form this compound. So in this case, Si has to be in the middle to form 4 bonds. So it already has 4 electrons. We can use crosses to represent the 4 electrons on silicon. And bromine will have to form bonds with the silicon 4 times, using 4 bromines. And bromine only needs 1 more electrons, so only forms 1 single bond. aerosol gases. So this is page 14 of the notes. There are two molecules shown for aerosol space. There's propane and there's 1112 tetrafluoroethane. You have to draw the dot cross diagram for these molecules. So just to remind you what is in the notes, you will find these structures in the notes. So this is propane, and to draw the dot cross diagram, basically all of these are single bonds. So you have to draw the three carbons bonded together by single bonds. Each carbon has 4 electrons. So there are two carbon-carbon single bonds, and of course there are hydrogens to finish the molecule. Each hydrogen forms a single bond to the carbons. So this way you understand the bonding in propane. And for 1112 tetrafluoroethane, in the notes is represented like this. So we have 4 fluorines, 2 hydrogens. So very similarly, can do the carbons. Forming a single bond and then adding the fluorine and hydrogens. Fluorine has 7 electrons, so don't forget these lone pairs. And hydrogens has only 1 electron. Okay. So you can use dot and crosses to distinguish between the electrons coming from carbon or fluorine or hydrogens. Those are not too difficult. Next, you have to explain briefly principle of a refrigerator. So how does a refrigerator works? Well, it relates to the expansion of liquefied gas and compression of the gas back into liquid. And so you have to basically be clear. Maybe you can draw a diagram if you want. This is the refrigerator box, and there's something taking place inside and something that takes place outside. So in the outside, we have a compression pump. So this is where compression takes place. And in the inside is the expansion chamber. And heat in the inside is absorbed in this process because gas expansion absorbs heat. So that's why in the inside it gets colder. And in the outside, compression of gas release heat. Okay, so that's why the back of the fridge is hot. Okay, so we can explain this in words. Compression of the gas takes place outside the fridge. This process releases heat. To the surrounding. The compressed gas, compressed liquefied gas goes into the inside of the fridge. And expands into a gas. You can say that gas expansion absorbs heat. From the surrounding. So it cools down, so the surrounding temperature drops. So you can say that in this cycle, heat is transferred from the inside to the outside. There are a few points here, right? So transfer of heat from inside to outside. And what happens to the heat when gas is compressed or expanded? Now don't worry about copying if you don't have time. All of these will be scanned and uploaded on Canvas. You can download my handwritten notes later. Not the best handwriting, I know. Then we have to consider these two molecules, propane and 112 tetrafluoroethane, and ask some questions about their molecular properties. For example, if they are polar or non-polar molecules. So the first one is propane. The structure is like this. Now, if we think about polar or non-polar, then we have to think about electronegativities. Carbon and hydrogen has a small difference of electronegativity. Carbon is slightly more electronegative, which means that in the carbon-hydrogen bond, there's a small dipole, delta minus, delta plus. But the molecule is a 3D shape, and it is completely surrounded by the hydrogens, the carbons in the middle, and it is freely rotating. These bonds can rotate around. So there is no fixed direction of positive and negative. Everything on the outside is the hydrogen, so it's slightly positive all the way around. Okay, so there's no overall net dipole in the molecule. It's all cancelled out by each other. There's the negative charged carbons in the inside, but very small dipole. Okay, so this is a non-polar molecule. This is no net directional charges. But for 1112 tetrafluoroethane, plus these are 3D shaped molecules. The fluorine has a very high electronegativity. F is 4.0. It's the highest of all the elements. So there's very large delta minus in the fluorines. Okay, but hydrogen is still slightly positive compared to the fluorine. So we definitely have a side which is more polar. This end of the molecule is more delta minus. This end is more delta plus. So there's a directional positive and negative charge. So this is a polar molecule. There's a net dipole. So there's a net dipole in this direction. Okay. This is the positive side. This is the negative side. So polar molecule, non-polar molecule. So once with this knowledge, you have to state the intermolecular forces present in these two molecules and indicate the strongest force. So for propane, which is a non-polar molecule, it will have London dispersion force. This is to do with the electrons being unevenly distributed within the molecule by chance and then forming some dipoles. And that's it. There's no polarity, so there's no dipole-dipole attractions. So for tetrafluoroethane, we also have London dispersion force. This is a force that is present in all molecules. But we also have a dipole-dipole interaction. Or dipole-dipole force, okay? Now, of course, this is the strongest force. And here we only have one, so it has to be the strongest. So this is to distinguish between polar and non-polar molecule. Yeah, non-polar only has under dispersion force. Do we have hydrogen bonding here? If you work out the conditions, then we don't have hydrogen bonding because the fluorine is not attached directly to the hydrogens. So then you have to predict which of these molecules has a lower boiling point. So because tetrafluoroethane has extra dipole-dipole interactions, so it should have a stronger attraction, requiring more energy to overcome. So it should have a higher boiling point. So propane will have a lower boiling point. It has weaker intermolecular forces. Part E, give 2 reasons why propane is not used as the coolant in the home refrigerator. So why don't we use propane as the gas in the compressor and expansion unit? 2 reasons. The first one is because propane is actually a flammable gas. Okay, so you don't want to have the risk of fire or explosion in the fridge. That's scary thought to have a propane is like a LPG, like petroleum gas. So having propane in your fridge compressing and expanding all the time with the sparks going on around it, it's like having a bomb waiting to explode, right? So the second point is because propane has a lower boiling point, so it requires more pressure to compress it to a liquid. Therefore, it's more dangerous, okay, and more costly as well. If you have a lower boiling point, then you need to compress it more at room temperature to make it into a liquid. So it's either more dangerous or it would be more expensive to build such a compressor. Okay, third question. Iron rusting in a sealed tube. So this experiment is conducted by having some iron wool stuffed into a measuring cylinder, inverted over some water to seal it up, so there's some air inside. The iron wool is slightly damp, so there's some water around. So the iron can rust and combine with oxygen in the air. Predict what happens to the level of water in the cylinder. So once oxygen is used up, then the water level has to go up. So because the air contains how much oxygen? Well, air contains 21% of oxygen. So that's around a fifth of the air's volume. So when all the oxygen is reacted with the iron, the volume will decrease by a fifth. So the water level rises up. So you can draw it here as well, maybe around a fifth of this. And here's the other 4/5. It should rise up about a fifth. Name three most abundant gas left in the cylinder after the reaction has completed and there is no further observable change in the level of water. That means that all the oxygen will have used up once there is no further observable change. The three most abundant gas left behind after this should be, the first one should be nitrogen, because nitrogen has not reacted and is still the most abundant gas. In this mixture left behind after the oxygen is used up, nitrogen would be at around 99%. Okay. The next gas that would be most abundant is the third most abundant gas in the air after oxygen, which is argon. Argon should be around 1% in this case. Usually it's around 0.94%. And the next one after this, we should have carbon dioxide. This carbon dioxide is the most abundant among the minor components. Should be around 0.04 to 0.05%, slightly higher than 0.03 to 0.04 because we have decreased the volume a bit. Of course, you can also suggest that there's water vapor, but we ignore this. Okay, of course, there's water vapor in above water, so we kind of ignore this one. But if you take into account water vapor, then it should be, water vapor would be maybe the second or the third most abundant. Okay, if it is saturated with water vapor, then maybe around 4% of the air can be water vapor. Okay, so if you vote water here as one of the component, then you can also get a mark. Okay, should be acceptable as well as an answer. Okay, so this question is a more difficult one. Study the boiling points of the atmospheric gases in the table in the notes, and you have to look at two sets of gases. Methane and krypton both have higher boiling points than argon. Okay, all these three molecules are nonpolar, so only attracted by London dispersion forces. Explain the reason for the higher boiling points of methane and krypton compared with argon. Okay, so there's a different reason for each gas. So you have to remember that in London dispersion force, the strength of the London dispersion force is dependent upon how many electrons there are in the molecule. So it is usually more electrons you have equals more chances of uneven distribution of these electrons. So you have stronger London dispersion force. Now we have to compare the number of electrons, therefore, for methane, for krypton against argon. So number of electrons in methane is 10, 6 in carbon, 4 in the hydrogens. Krypton is 36. You can find this from the table. Argon is 18. You can also work out the molecular mass if you want, or the atomic mass. That's also related. So methane and krypton have higher boiling points than argon. Now it is clear to say that because krypton clearly has more electrons than argon. So the reason for the higher boiling points in krypton is most likely that because there is more electrons. Actually, what about, was it double? Number of electrons. So there are more electrons in the krypton atom than the argon atom. So there's a higher chance for electrons to be unevenly distributed, or there's higher chance of uneven distribution of electrons. So stronger London dispersion force. So that's half of the question answered. The other half is to ask the question: methane has less electrons than argon, but it still has a higher boiling point. Why has methane got a higher boiling point? But then in this case, we have to consider the shape of methane. So this is methane versus argon. Shape of methane is a tetrahedral molecule, like this. So it has a 3D shape. So the electrons can kind of travel around the molecule and have more chances to become unevenly distributed compared to the argon, which is a spherical atom. Okay. The shape of methane is tetrahedral. It is more uneven. Or you can say it encourages uneven distribution of the electrons. More than the spherical shape of argon atom. So basically encouraging the uneven distribution of electrons among the more complicated shape of the molecule. So even though there are less electrons in methane, then it can still has greater chance of delta plus delta minus, leading to overall larger attraction forces. So these considerations apply to molecules with similar number of electrons. If they are too far apart, for example, krypton and methane, then krypton has a higher boiling point than methane, I think. Because there is more than 3 times the number of electrons. So then it's overriding the factor here. Okay, we're doing well. So rocket science. Rocket science, we have to consider some molecules here of nitrogen. We have to classify them into elements and compounds. That should be easy. Nitrogen is element, and these two are compounds. Then we have to draw a dot cross diagram to indicate how these molecules bond together. Okay, so for nitrogen is a group 15 element, so 5 electrons in outer shell. So it needs 3 more electrons to get 8 electrons. In that case, we need to form 3 bonds. But only 2 atoms, we cannot have 3 single bonds, so it must be a triple bond. Okay, so in that triple bond, and then we will have 8 electrons each. So we can also draw it like this. In the line structure, of course, you have to show the dot cross diagram as requested by the question. N2H2, we have 2 nitrogens together, but now we have 2 more hydrogens. The hydrogens are attached, 1 to each nitrogen, like this. And they can form a single bond to the nitrogen. So in this case, the nitrogen can form 1 less bonds between themselves. There should be 5 electrons each, okay, like this. So this time a double bond between the nitrogens. And lastly, N2H4 with 2 nitrogens forming bonds, but now 4 hydrogens. So in this case, we already get 2 electrons from the hydrogens. So because it needs 3 more bonds, 3 bonds, so we already have 2, so it only has to form a single bond. And then there's 2 more electrons, like this. Okay, so this is N2H4, which is hydrazine. The question then says hydrazine is a fuel for rockets. In the rockets, we use hydrazine in the liquid form, and this is decomposed to form nitrogen and hydrogen gases. And these gases then propel the rocket forward in space. So you have to remember that in space there's no oxygen, so you cannot have a fuel and expect the fuel to burn by itself. So this is why hydrogen is useful, because it is a liquid and it decomposes to form gases. So you can push the rocket forward by having a propelling gas behind. Okay, so we have to write an equation to express this reaction. Okay, and be sure to balance the equation by adding the numbers in front of the chemical species. Okay, so this is to use the information given in Word and transform this into writing an equation, a practice for doing that. So you have to read the question carefully, then you can see that it's hydrazine itself that decomposed into nitrogen and hydrogen. So somehow hydrazine is forming nitrogen and hydrogen. So we need the formula for all these. Hydrazine is N2H4 as given in the question. Nitrogen gas is N2, not N. Hydrogen gas is H2. Okay. So then we need to balance the equation. There are 4 hydrogens here, but only 2 on this side, so we add the 2 there. Okay. So this is the answer. If you wanted to add the state symbols, you can do it as well. N2H4 is in liquid form. So this is L. And then these are gases, so they are G. One of the reasons to use hydrazine on the rockets is because it is a liquid with a boiling point of 104 degrees, which avoid the risk of having pressurized steel cylinders containing liquid gases as the fuel, because it's high pressure and it's outer space, so it's risk of explosion. So based on the structure of hydrazine, explain why it is such a high boiling point liquid, 114, okay, more than water. So illustrate your answer with a sketch of how the N2H4 molecules attract to each other. So here we have a bonding which is similar to water. Okay, this is a hint because it has very high boiling point, and it hints to hydrogen bonding. Okay, so you have to identify that there is hydrogen bonding in N2H4 because it satisfies the requirement. So you can draw a structure of N2H4 here with the lone pairs on the nitrogen, and you have to draw another one next to it. One here. So then you can show that the lone pair of a nitrogen, which is delta minus, attracts the delta plus of the hydrogen on that side. And the delta plus here can also be attracted by the lone pair of nitrogen there. Okay, so these are the hydrogen bonds. If you want, you can draw another one there. There are lots of hydrogen bonds that can be formed between the hydrazine molecules. And on average, each hydrazine can form 2 hydrogen bonds because it is limited by the number of lone pairs on the nitrogen, only 2 lone pairs, although you have 4 hydrogens. So it can form a maximum, it can form a maximum of 2 hydrogen bonds per molecule. Okay, so this is also why it has such a high boiling point, because you have 2 hydrogen bonds per molecule as opposed to just 1. Okay, so much higher boiling point in this case. So using calculations, we can appreciate the propelling power of using hydrazine as a rocket fuel. The first one is to calculate the relative molecular mass of hydrazine. So that's very easy. So for N2H4, we just calculate the mass of nitrogen, and we look it up in the periodic table. It's 14.0 times 2 nitrogens, and 4 hydrogens, 1.0 times 4, and that's 32.0. Second, number of moles in 1.02 grams of hydrazine, which is 1 cm cube in volume. Okay, so the density of hydrazine is 1.02. Okay, so moles, we are given a mass, so mass divided by is mR. So 1.02 divided by 32 would be 0.0391 moles. Okay, so in 1 cm cube of hydrazine, there is 0.0319 moles of hydrazine. That's easy up to this point. Then we have to deduce the total number of nitrogen and hydrogen gases that are produced when 1 cm cube of hydrazine decompose. So remember, we had this equation which we wrote down this one. So you can see that for 1 mole of hydrazine, okay, we will form together 3 moles of gases. There's a 1:3 ratio. So the total mole of gases equals 3 times the moles of hydrazine, which is 0.30319. Okay, so that gives us 0.095 moles of N2 and H2 together. And these are the gases which will propel the rocket. So fourth question, now really think about the question of propelling. Assume the rocket is flying at the space station near the moon. So the temperature of that outer space is around minus 100 degrees, and the pressure will be almost vacuum. Under these conditions, okay, we can actually use the ideal gas law to calculate that 1 mole of gas would occupy a volume of around 2 times 10 to the 20 cm cube, so much bigger volume than on Earth. Calculate the volume of gases produced when 1 cm cube of hydrazine decompose into the gases. So this is decomposition of 1 cm cube of hydrazine. So we just have to work out that, remember that 1 cm cube of hydrazine gave 0.095 moles of N2 plus H2. So 0.095 moles of gases has a volume of 2 times 10 to the 20 cm cube, which gives us 1.914 times 10 to the 19 cm cube. So the volume expansion ratio, how many times has the volume expanded? The volume expansion is going from 1 cm cube to 1.91 times 10 to the 19 cm cube. So that's a factor of 1.91 times 10 to the 19 times. So they are expanded by 10 to the 19 times.